Now this session and the next, this board, three whole sessions on this diagonalization technique, which is a critical component in the proof that the language A suffix TM is undecidable. So we need to become familiar with this diagonalization technique created by Cantor in order, as a stepping stone towards proving this famous theorem that A, capital A suffix TM, that language is undecidable, which is effectively the halting problem. The halting problem has no solution. There's no algorithm that can decide, that provides a solution to that problem, which is famous. Alright, now at the very end of previous session we introduced a definition, 4.12 in your text, and it's actually a whole bunch of definitions about the nature of functions, actually, mappings, and we'll give a whole series of labels to different kinds of mappings between two sets. So, that's what a function is anyway, right? What is a function? It's just a mapper between one set and another. So you have f colon, f is your function, colon, capital A, arrow, capital B. Where do we have written those somewhere? Do we? Yeah, here. So that's the standard way of writing a function. A function is some kind of you associate a member, or you connect a member of your first set A to a member of your second set B. Now, association, that's a rather vague term because set theory is very, very, very general. But so your function, if you input an element of big A, say little a, so f of little a would get associated with some element little b of set big B. That's the here this kind of thing. So you take some element of A, call it little a, you plug it into that function, and you'll get some member of big B, we'll call it little b. So f of little a is equal to little b. That's what a function does. It maps members of one set into members of another set. Now you can map in various ways, and each these ways, the important ones, they get labels. Certain kinds of mapping. So that's what this definition is about, and we will need this knowledge, these various kinds of mappings, for understanding how to do this diagonalization technique. So there's quite a few stepping stones. So we need to go through it. All right. Now, one kind of mapping is called one kind of function. It's the same thing. A function is a mapping. Right? And what's a mapping? Well, it's this sort of thing. You take an element of your first set and you'll map it, or the function will give you an associated member of the second set. Right? F of A is B. So function and mapping, same thing. Alright, now function or mapping is said to be one-to-one, also known as, aka, you can write it this way, just the number 1 colon 1, sort of saves you the effort of writing out all these letters. You just 1 colon 1. So a one-to-one mapping, what does that mean? One-to-one means that, well, in a sense, it's not many-to-one, put it that way. A many-to-one, you could have FA1, FA2, FA3 all mapped to B. Okay, that would be many-to-one. So You can visualize it like here's your B, and here's A1, A2, A3. So you've got like three arrows, three connections, three lines, if you like. All of those three elements map to B. That's many to one, or 3 to 1. Now 1 to 1 is when there's only one line going to B. Right? So if you have 1 to 1, you cannot have more than one element in A, set A, that maps to that element little b. Right? Because then it would be many to 1. So many to 1, 1 to 1 are opposites. They're mutually contradictory. Alright, so if you have f of A is not equal to f of B, and it's 1 to 1, well then your A and B have to be different. That's a consequence of 1 to 1. Now you can do it the other way around. So if you have two different elements in your set A, now it's a bit confusing because here little b belongs to set B, but the little b here, both little a and little b here both belong to set A, so don't be confused. So if you have two different elements in your set A, and then you map them 1 to 1, then the two elements you get in set B, they'll be different. Right? Because if they were the same, if this actually equaled that, if they were the same element in set B, well then you've got many to 1, well you've got 2 to 1, right? And that's not 1 to 1. Alright, so that's 1 to 1. I can draw that in the form of a picture. Like here are two sets in sense of Venn diagram. So this would be 1 to 1. Okay? That one maps to that one maps to that one. And this one doesn't get mapped at all, let's say. Or I could do it another way. Say this has 2 elements and this one has 3. Then that's 1 to 1. Okay? In fact, I'll use this diagram, it's quite useful. Alright, now the concept of onto. So a function or a mapping is onto, what does that mean? Well, that means that every element in your second set, your big B here, is mapped to. In other words, there's like a line. Now, in this case, this mapping here is not onto, because you have this, what's the word? Straggler? No? Disconnected. Isolated. So you have this isolated member here, not connected. Right? So this particular mapping is not onto, because there is a member of this second set B that is not mapped to. When you have an onto mapping, every element of your second set BB is mapped to. Okay, there'll be a line to each element of B. That's onto. Okay. Right, now combine these two. Say you have a mapping now that it's both 1 to 1 and it's onto. Well, if you think about it, that means that those two sets, big A and big B, if that mapping is 1 to 1 and onto, those two sets, A and B, big A, big B, have to be the same size. Okay? Well, assuming they're finite. Can you see that? Can you see that logic? Like, so it's obviously 1 to 1, right? 1 to 1, 1 to 1, 1 to 1. It's not many to 1. And this mapping is onto, because every member here is mapped to, okay? But it satisfies the two conditions at the same time. It's 1 to 1 and it's onto, right? Well, therefore, these two finite sets, they must have the same number of elements. Okay? So in other words, the size of those two sets is the same. Okay, so this combination of your mapping that is at the same time, so two conditions. The mapping is one-to-one and it's onto, right? That means your if your mapping is one-to-one and onto, then the two finite sets, they have the same size. They have the same number of elements. Okay? Now, this kind of mapping, Sipser calls it a correspondence. Well, yeah, I've heard that term used. The mathematicians tend to use like AKA, also known as bijection. That's the more standard term in pure mathematics. So mapping is very often used technique in algebra, for example, in pure mathematics. So this term bijection tends to be used. Now, if some of you guys are going to keep following me for years, and you get up into PhD level math and math physics, I'm trying to get you to be as familiar with thinking in pure math terms as in physics terms. So I'll give you the math terms. So one-to-one, standard math term is injective. Right? So if you see this term injective, just think one-to-one. And onto, the math term is surjective. Sur, that's from the French. Sur just means on or onto in French. I speak French. Mes livres, my books are sur, on la table, on the table. Mes livres sont sur la table. My books are on the table, on. Okay, so sur, where is it? Let's see it. Yeah, sur, onto, surjective, on, because invented by the French, great mathematicians.